Hi, everyone. It's a pleasure for me starting here. I am David Medina. I'm a research in Universidad de Magallanes in Punta Arenas, Chile, in the extreme south of the world. And today, take about of plastic ML tool that is a machine learning tool for discovering and optimizing plastic enzymes. This is the big wall of the tool. And so, for context, we have a very global problem right now. That is the plastic contamination that it was explained. It was the previously talker. That obviously we had found this problem in mountain, deserts, farms, in a lot of different landscape that could be seen. And some different statistic, 12 million tons of plastic find its way into the ocean every single year. Every minute of every day, a truckload of the plastic is dumped. And the 73% of each liter world is plastic. So there are different types of plastic, but it's possible to classify it in two very big types that is associated with thermoplastic that you can, I have in here, and thermoset. And in particular, for example, only 6 thermoplastic types represent 87% of the type of the plastic that is associated. For example, PET, for example, PA, for example, PA, so on and so forth. So different strategies can be implemented to address this problem. In particular, the problem of the plastic pollution. In particular, there are two options right now. The bioplastic has eco-friendly polymers that some case, as for example, PLA, PBAT, and other, but the industrial is still economically non-viable right now compared with the fossil origin plastic. And right now, another strategy is the circular economy that you can see it's every day. That, for example, you design, production, retransformation, distribution, and offer. But despite of the different strategy or different efforts, the challenge is persists. It's very complex. So, biotechnology approach associated with this problem is associated to biodegradation, bioremediation, and the use of plastic degrading enzymes. And for example, the use of microorganisms that have been employed, that enzymes and biological process to decompose some plastic and have been encountered in the environment. And some examples of these microorganisms have been PET or PA's plastic degradation. Based on the increment and the high screening throughput methods or strategies, the increase of the information about the sequence or about of the different information literature have been increased exponentially and facilitated the application of machine learning and data-driven approach. In particular, you can see a classical pipeline in here about of data-driven platforms that start is considered in the collecting data sets, apply numerical representation to train a predictive model, and then obtain the performance and use the models to, for example, evaluate mutations, to evaluate unknown enzyme sequence everywhere. And in particular, machine learning have been used in different applications in biotechnology, for example, for protein engineering, machine learning assisted evolution, among others. And the idea of this tool is how to incorporate these strategies in a unique platform to assist or to address the study of unknown of the plastic degrading enzymes. For this, we are working on plastic ML tools that you can see there have different characteristics. In particular, in cyclicization, you can represent different properties statistics. We have collected information from different integrated data sets, database, and resources in the literature. And also we have integrated different machine learning strategies, in particular for classification model, for evaluating the EC number, the gradient, if the enzyme is the degrading enzyme or not, the evaluation of type of plastic, and also for predicting more numerical properties like thermostability, solubility, and also the catalytic optimal temperature for catalytic activity. That is very commonly for the use of PET in the case. And also explore, this is explore because it's very now, the discovery of novel enzymes based on generative approaches. And so the first is the Plastipedia. We are not very original with the name, sorry. Plastipedia is our database that collect information from datasets, database, and different literature available. And in particular, we have the first step is the process enzymes that we have collect information about the gene ontology. We can use different tools, different strategies that have previously reported by of panels in here. And also we have complete the information, the characterization using domain, family, simplify in particular, and also evaluate different characterization of the enzyme using physical properties, experimental properties, and different information that are available in database like Brenda, for example. And also we have a plastic evaluation that evaluate what is the type of plastic that is possible to degrade. Yeah, and we have implemented generalizable ETL, extra transformer load in our database that have facilitated the collected of more than 600 plastic degrading types actually. Yeah. Then we have implemented a generalizable sequence-based approach for training classification model that it's have 3 steps. As you can see in here, the first step is an engine preprocessing that we have the protein sequence enzyme, and we have explored different numerical representation strategy. That is classical Hall encoder, physicochemical encoder, sorry, fast Fourier transformation, or protein language model. That is very interesting for all. Yeah, and with the coded data set, we explore classical division between training and independent test data set. Then, with the trained data set, we explore different machine learning algorithms with different hyperparameters to evaluate what is the most stable combination of numerical representation strategy with machine learning, supervised learning algorithm. Evaluate using different classical metrics like accuracy, precision, or recall, because it's a classification model. And with this, we repeat iteratively this process n times to create a distribution in this case. And with this distribution, we apply the next steps. That is a statistical based method for selecting the most stable approach. And with this most stable, we apply a tuning processing based on Bayesian approach. That's with this, we use finally the independent data set for evaluate the last metrics and to select what is the best strategy to design this model. With this, we have evaluate different binary classification model, in particular for different PET, PAs, HB, and 3 more type of plastic. In particular for PET, as you can see here, the precision and accuracy of different metrics, that you can see training and validation, in particular for different supervised learning algorithms. And you can see, for example, the methods like self-correcting machine and random and assembly-based method achieve better performance in more stable compared to method like Gaussian process, for example. Yeah, and the best strategy in the case of the PET was the application of supervector machines, a supervised learning algorithm combined with a sigmoid kernel. And for example, you can see the performance in here is a 96%. Obviously, it could be interesting, but the problem here is the low-end datasets. And for this, we are working integrating, for example, techniques for transfer learning or another strategy that could be support how to work with low-end datasets in theory. So alternatively, with the collected peptides, peptide sequence, we are exploring different generative learning to try to generate the novel potential enzymes. In particular, we are very interested in the variation autoencoder because we need to design similar sequence. Yeah, and in the case of generative adversarial network, could be very interesting. But they explore, for example, neural language model of robust could be interesting, but it's not all the first focus. Yeah. Alternatively, with the same, okay, yeah, okay. Alternatively, with the same focus, we have implemented a binary classification model for the optimum temperature optimal for catalytic activity. In particular, we have collected all information from Brenda database and split the information based on the PET model here. In other words, we have collected information of the PET and make classification for positive or negative example associated with a threshold that is a temperature higher than O threshold and lower than O threshold. And based then we have implement the classification model, and we have performance for this model of 85% of precision. So with this model, the next step is, okay, how we train a regression model to predict particularly the temperature optimal for catalytic activity. And with this, it's possible to combine this method with machine learning assisted evolution to assist possible evaluation of single permutation or to others, improve the temperature associated for PET degradation enzymes. Conclusions. We're implementing right now plastic methods, and we have finished our database with more than 1,600 records. We have developed more 6 binary classification models for different types of plastic, and 1 binary classification model for temperature optimal. Currently, we are working on the predictive model of the temperature optimal, and obviously, we need to improve it because the prediction of the temperature optimal is so complicated right now. So working in process also is the how to incorporate generative learning. Obviously, the bulk and incorporation of additional predictive tools and a future deployment during this year. Obviously, there are a lot of people in here, for example, all advisors or the advisor institution, and for attention, thank you so much.
Questions? Any questions online? No?
Okay, thank you for your talk. I have a question. When you're using the embeddings,
yes,
are you using the per protein or per residue?
But
okay. So are you thinking about using the residue?
No. We want to explore it, but we don't have the computational costs associated to doing the models right now.
So the idea is to identify, to optimize the function of this protein.
Yeah, but this is another step associated with a specific detecting what is the single permutation that, or the specific residue that improve the activity or decrease the activity, but in combining with increase the solubility or maintain the solubility on increase the stability and decrease the stability. It's a synergy of the different properties.
Okay, thank you very much.
Sure, maybe a follow-up question. So as you know, when you are trying to extract embedding from these language models, right? These language models give embeddings per residue. And when you're using protein, so you have to kind of come to a fixed representative. So are you using some type of averaging to get the per protein embeddings? How do you do it?
No, sorry, I don't understand the question.
So for example, for Protify, for each residue, you get 1,024 features, right? Embedding size. But your proteins can be of varying length, different lengths.
Yes.
So, but your machine learning model or apparatus won't take features of different length. So you have to come up with the fixed features. So I was wondering how you're doing it. You're averaging per protein?
Yeah, but in this case, they're using, for example, the protector model and using a reducer method to optimize the specific number, the equal number of the feature for all proteins. Is your question? Yeah.
Any other questions? Just a comment. My younger daughter, who is a rising sophomore, she was working in a lab that degrades, plastic. Again, if you ask me what she does, or how did she do it, I have no clue. But I think it's very interesting and very exciting. She had her own pet project where she was trying to degrade cardboard boxes. So she was growing bacteria to degrade cardboard boxes.
Thank you so much.
All right. Thank you.